parts of secants in the picture, but more often than not, it's going to be that full secant drawn like that that you'll see in the picture. So we're going to see how a secant would help us with our formulas in a second. We're going to focus on Theorem 1 and Theorem 2, which are referring to angles on this side of the page. And when we turn the page, we're going to be talking about 3 more theorems that are going to be working with trying to find the lengths of segments. So first, we're going to learn 2 new ideas about angles, and then we'll switch to the segments. So this first one, the measure of an angle formed by 2 lines or segments intersecting inside a circle. This is our first keyword here. We're going to have one formula for where they intersect inside, and then another for when they intersect outside. So if they're intersecting inside of a circle, that angle is half the sum of the intercepted arcs. Half the sum of the intercepted arcs. So if you see this scenario, whether these are segments or they've been continued out of the circle, lines, whatever, if you have this crisscross kind of shape inside of your circle, so an angle is formed, then you're going to have 2 intercepted arcs. You would add these 2 together and divide by 2 to figure out what the angle measure is. Now look very carefully. When I draw these chords or parts of secants or whatever you have here, do you guys see how I actually have 4 arcs total? It's been chopped into 4 arcs. How do I know which 2 to use? How do I know which 2 are supposed to be finding that angle? Crickets. Okay, notice how I included the word intercepted here. Right, intercepted arc. So when I'm talking about this angle right here, do you guys see how this blue arc right here is intercepted to this angle? And then if I think of vertical angles over here, these angles are related to each other, right? They're vertical angles, so they should be equal. So you could also consider this to be an intercepted arc of a congruent angle using the vertical idea. So if you guys want to, what I did when I was younger is I would draw a line like this. They all have to be lined up. So these 2 arcs with the angle, if you can draw a line all the way through them, those are the pieces you would use in this formula. If I was looking for this angle, these 2 arcs would not be in line with this one. Okay, to find this angle, I'd have to use those 2. So just think about the idea of intercepted. All right, it has to be the arc that's intercepted between these 2 congruent angles because they're vertical. Or you can draw that little line to see that they line up. All right, so that's something to avoid making a mistake on. Now I have written the formula in words, but I also want to write it more of a summary here. So the angle would be equal to big plus small divided by 2 based on the drawing that I have there. So just as a little formula kind of format, I have the summary of this formula written here. So the angle is equal to the big arc plus the small arc divided by 2. Now does it matter if I do big plus small versus small plus big? No, because it's commutative. So I just like to write it big plus small in that order just so it's easy to organize. Okay, so that's our first one. When it's inside, you add the arcs and divide by 2. What do you think happens when the angle is outside? You're subtracting. Same idea. So this time, if you have lines or segments intersecting outside of a circle, the angle is equal to half the difference of the intercepted arcs. So now when your angle is being formed outside the circle, so this is where you have 2 secants, like this. You could have 2 tangents, like our clown hat rule kind of scenario. Or you could have 1 tangent and 1 secant, like in this picture. But all of these angles are outside of the circle. So when you have something like that, this one is going to be big minus small divided by 2. So it's the same kind of formula. You just have to see whether the angle is inside or outside the circle, and that tells you whether you're adding or subtracting the arcs. Now for this one, does it matter which arc comes first? Yes, because subtraction is not commutative. So this one you have to make sure that you are subtracting the smaller arc from the bigger arc. Right? Kind of think of it going in towards the angle when you're doing your subtraction. Okay? So big minus small in all of these scenarios. And you can see which arcs to use because they're going to be the ones that are inside of these angles. Okay? So those are our two formulas. We're going to practice using them in a second. Does anybody have any questions about this before we apply them? Okay, let's take a look. Just 4 for now. We'll have plenty of additional practice on the 3rd page. All right, is this an inside angle or an outside angle? Okay, so am I going to be adding or subtracting? Okay. Now, for this one, we're not trying to find an angle. We actually know what the angle is. We're trying to find one of the arcs. So this is just being careful with the formula. The angle is 20. Right, so the angle is what we know. The formula says you do the big arc minus the small arc divided by 2. So I just look at the formula, I plug in everything that I know, and I solve for what I don't know. Okay, so the angle's on the far left, then you plug big minus small over 2 on the right side, and then we solve. So this one you have to do a little bit of algebra. Not too bad though. Should end with y being equal to 30. Okay? Alright, what about this one? Is this inside or outside angle? This is another outside angle. This is a tangent and a secant, intersecting. So this is going to be add or subtract? Subtract. So the angle is x, that's what I'm looking for. I do the big arc minus the small arc divided by 2. This is just a straightforward, plug in your calculator, find the numerator, divide by 2. What do you get? 34. Okay. Is this angle inside or outside? Inside. So am I going to be adding or subtracting? Adding. So then the angle is equal to the big arc plus the small arc divided by 2. So again, that one's pretty straightforward. You get 110. And again, I know if you want to, again, you can draw the sign. You can see that the arcs and the angle are all in a straight line. They all line up, so I know I have all the correct information. And then this one is an outside angle. So you do 30 equals the big arc minus the smaller arc divided by 2. Math. Oops, sorry. There's an alternate way to solving that one. Yes? Oh, hold on. So since we're practicing the formulas, you can see how the formula would apply. I mistakenly put this example here because there is a more effective way of solving that. You can just do 360 minus 150. But I was just trying to get more examples of that, and I didn't realize that that one was so easy. But with the formula, you can get the same answer anyway. This is how you would apply that. I've changed it for next year, so it's not quite as straightforward. But if you saw something like this, you could obviously just do 360 minus 150. It's totally fine. I just wanted to show more practice for that formula. All right, so everybody see how we use the formulas? Everybody's okay with that? Okay. Before we move on to the segment ones, I want to summarize everything that we know about angles. And that's this little box right here. This is going to be our little treasure box of everything that we've learned so far from day 1 about all the different types of angles. We've learned 4. Okay. Our first one is when the vertex is at the center. So that's a central angle. I'm going to write relevant vocabulary above the box and then draw a little picture underneath. And then inside of the box, you're going to tell me what the relationship is between the angle and the arc. So first central angle, what's the relationship or the rule that we use? The angle equals what? The arc. This is our relationship that we learned from day 1. If it's a central angle, the angle would be equal to the arc. On day 4, last class, we talked about when the vertex is on a circle, which mostly applies to things called inscribed angles, but we also have that other one with the tangent and the chord. So the two pictures you could draw is your inscribed angle, and then when you have a tangent and a chord meeting, like that. But in any case, whether it's inscribed or that other type, if the vertex of your angle is on the edge of the circle, what's the relationship? It's 1/2 of the arc, half the arc. So from day 1, central is equal to the arc. From day 4, the inscribed angle or this type of angle is half of the arc. Those are the first two. Now we're learning our final two in this lesson. So I'm not going to draw those pictures. Those are in the notes above. Okay. So what is the formula when the vertex of the angle is outside of the circle? Angle equals what? Outside. Big minus small divided by 2. It's a rule or formula that we would use. And then our last one, our fourth type of situation here is when the vertex is inside the circle but not the center. I know technically this is still inside the circle, but when I say inside the circle, I'm referring to any other situation besides being at the center. So what would happen for that one? Angle equals big plus small divided by 2. Alright, so that's a summary of everything that we know about all the different types of angles you guys will be working with in circles. Just make sure you're able to visually notice the difference and remember how you would solve for arc or angle measures depending on which one they're asking for. Okay? Now we're going to switch from angles and talk about segment lengths. We have 3 formulas for segment lengths, and it depends on what kind of segments they've given you or that you're working with. Our first one is when you only have chords. Right? So you have chords that are intersecting inside of the circle. This is a very basic and easy to use formula. So I'm going to give the worded definition of the rule and theorem, and then I'm going to write it down as a variable type formula so it's easier to see what it's talking about. So when 2 chords intersect, the products of the chord segments are congruent. Products, meaning multiplication, the products of the chord segments are congruent. So again, this is a very simple formula. All it's saying is that the 2 pieces of one chord, see how they've chopped the chords, they've chopped themselves into 2 pieces. If you multiply the pieces of one chord together and then multiply the pieces of the other chord together, those should be the same. So if you're writing it as a formula in here, you could do A times B, and then you could do C times D, and those should be the same number. Notice this is multiplication, right? Do the chords themselves have to be congruent to each other? No, right? See, you can clearly see the blue one's a little bit shorter than the purple one. So it's not saying the full lengths are equal. If that were true, then when you added them, they would be equal to each other. This is multiplication, okay? So the chords do not have to be equal in length. They're just saying that if you multiply the pieces together for each chord, they'll be equal. Okay? So that one's really big. You'll see. Using that one's really easy. All right, these next 2 are a little bit more complicated, especially in the wording. That's why they're a little bit longer. So theorem number 4, whatever, it's more of a formula than a theorem, but whatever. So when you guys have 2 secants, if 2 secants are intersecting outside of a circle, the products, this is multiplication again, the products of the full secants, plural, full secants, and their outer segments are congruent. The products of the full secants and their outer segments are congruent. I'm going to summarize all those words for you, and then I'll write it in a formula that kind of matches that diagram here. When they're saying you're doing the products of the full secants and their outer segments, a way you can summarize that is by saying full times outer equals full times outer. And these are lengths. So for one of the secants, you're going to find the full length of the secant and multiply that times the part that's hanging out of the circle. You're going to do that for both of the secants, and they should both be the same. So you take the full length of the secant times the part that's outside, and then for the other secant, you do the same thing, full length times the outside part, and those should be the same value. So in this circle, in this diagram over here, how would I apply that? How would I write that as a formula based on what I have in this picture? What's the full length? Full. What's the full length? W plus X. And then what's the part that's hanging out of the circle? So you multiply the full times the outside part is equal to, and then do the same thing for the other secant. What's the full length of the other secant? And then what's the outer part? So this is your kind of representation of the formula in variables. So you do the full length times the outside part equals the full length times the outside part for both secants, and they should be equal to each other. Sometimes they'll give you the full length outright, so you don't have to add the pieces together, so make sure you're looking for that. I'll show you some examples on the next page. But this is the summary of that idea. Full times outside part or outer equals full times outer segment. Okay? So that's when you have two secants, and then we have one more. If you guys have one secant, one tangent, it will work this way. The tangent squared, so you're going to square the tangent. The tangent squared equals the product of the full secant and its outer segment. Tangent squared equals the product of the full secant and its outer segment. This carries through some information from the previous theorem. So for the tangent, can you identify which one is the tangent in that diagram? T. So you're going to square that. If you see a tangent, you would square that. Okay? And then whenever you see a secant, whether it's this formula where it's only secants in the diagram, or it's a tangent and a secant, anytime you see a secant, you do the same thing, full times outside. So how would I represent the full length of the secant? And what's the outer segment? There you go. So anytime you see a secant, whether there's one or two of them, you're always going to do the full times the outer segment. But for a tangent, you would just square it. The reason why it's tangent squared, you're actually doing the same thing as you would for a secant. For a secant, you do full times outside part. But for a tangent, isn't the full length of the tangent and the outside part the same? So we're really doing the same. We're still doing full times outside, but for a tangent, both of those things are the same. So if you multiply them, that's why it's t squared. So it's really the exact same formula as this one. It's just represented different because the tangent's full length and outer segment are the same. So it would be t squared. Okay? So those are our segment formulas. We're going to do several examples here on this page, and then the third page that you guys have in your notes is a scramble of angles and segments all mixed together. So you guys will be working on independently to see if you can catch which formula goes for each diagram. Alright, but for this one, let's get started. Which theorem would I use for this scenario? The one at the very top, theorem 3. So all you would do, it's very simple. Whenever you see two chords crisscrossing, you would say the two parts multiplied, so x times 4, written as 4x, would be equal to 6 times 2, which is 12, and then you divide and you get 3. Less than 10 seconds and you're done. Moving on. Is everybody okay with that one? Okay. This one is your two secant situation, which is the theorem in the middle. So remember, this is the one where you do full times outer segment equals full times outer segment. So what is the full length of the first secant? 14. And what is the outer segment?
6.
And I would set that equal to the exact same thing on the other side. What's the full length of the other secant? This one on the right. I'm going to write it in standard form, x plus 5, but it doesn't technically matter. And then what's the outer segment? Okay. So once you write out the formula, we're going to simplify it and then solve. So 14 times 6 is 84. When I distribute the x, I get x squared plus 5x. What are we going to do? Factor. So you're going to pull the 84 over, so it's in the standard form of a quadratic. And then we're going to factor this. Now, my other class was shell-shocked. Had never used their calculator to find factors before. you guys know how to find factors in your calculator? No? Oh my goodness. Okay.
No way.
Calculator.
2004.
Because previously the numbers that we've been factoring have been very simple. When the numbers get bigger or less familiar, it's nice to have a tool you can use to find factors. So everybody hit the y equals button in your calculator, as if you're about to graph something. When you guys are trying to find factors, two numbers that multiply to get a particular number, which is what we're doing, we're trying to find two numbers that multiply to get negative 84. You're going to type in the first y equals equation box, you're going to type negative 84 divided by x. The variable x is next to the alpha button, so if you just hit the one right of that, you should see negative 84 divided by x in your, or y equals negative 84 divided by x. Now you're going to hit second graph. Second graph gives you a table of values. All the numbers that you see, the x and the y, are numbers that multiply to get negative 84. You're going to scroll through until you find the ones that add to get 5. Those are all numbers that multiply to get negative 84. You only want to find the whole numbers that add to get 5, please. Should be negative 7, positive 12. If you guys were scrolling and you got to negative 12, positive 7, and that adds to get negative 5, just switch the signs of the numbers and you're good. Yeah, if you accidentally start scrolling in the wrong direction, it's fine. Just if you got to positive 7, negative 12 first, just switch the signs and you'll be fine. Okay? So if we're unfamiliar or bigger numbers, you guys can use that trick if you want. Okay. But once you guys factor, whether you use that trick or just do it experimentally like you've probably done in the past to start dividing by stuff, whatever. When you get here, what do? I'm trying to solve for x here. What do? I have factored. What do? Come on, guys.
Go with the positive option.
No, what do I physically do in order to solve? You set each factor equal to 0. And so the results would give you what? Positive 7 and negative 12. Now, anytime you guys are factoring, you will get two answers. They may be the same answer, which is really one. But if you get two different answers, you always need to make sure that you're checking in any situation. Would both of those answers work? No, they would not. Does it make sense? There are two things you guys want to check for. The first one is, does it make logical sense? That's the first thing you want to check for. So if I plug negative 12, would it make sense for a segment to be equal to negative 12? No. Okay? So negative 12 is ruled out. If, however, you guys are working through with your answers that you got from factoring, bless you, and they make sense, like no sides are negative, no sides are 0, whatever, if they make sense, you still need to check to make sure that they're equal the way that they're supposed to. Because you can get a number that's not negative or 0, but it still is an incorrect answer because it doesn't work out with the formula. So always be double checking. Your answer is just 7. Okay. What would my formula look like for the next one? Z squared equals 16 plus 8 times 8. So the tangent squared equals the full length of the secant times the outer segment. So when I multiply those together, I get 192. And you're going to take the square root of that and then simplify. Here's another example where you can use your calculator, that little trick I taught you. If you guys want to figure out what the biggest perfect square is, you can do 192 divided by x and find the factors and look for the biggest perfect square in the table of values. What's the biggest perfect square that is a factor of 192? 48 is not a perfect square. It's 64, and then what's the other factor? 3. So that would simplify to 8 root 3. Okay? Alright, let's keep going. How would I do the next one? Be prepared to do the entire next page independently. So be using this opportunity to ask questions on how we do these. So how would I do this one? 3 times x equals 9 times 5, which is 45. Divide. know you can do this.
15.
Thank you. All right, what about this one? This one, please be careful. Is this theorem 3, 4, or 5?
I don't know.
Do I have 2 chords, 2 secants, or 1 secant, 1 tangent? I have 2 secants. Both of these line things, right? They're going to touch the circle twice. So this is theorem 4. You're going to do full times outside equals full times outside. So who can tell me what the formula would look like? What? Yes. What is the full length of the upper secant? So why are you, I heard some people subtract, I heard some people try to add. No, right? The formula is full times outside equals full times outside segment. So if they tell you what the full length is, there is no addition or subtraction or anything like that. You just use the full length times the outer segment and you're done. So this is really 3x equals 15 times 5, 75. This is really what your formula is. And you would just continue by solving. And you would get 25. So when you see the bracket's really important there. When you see the bracket from one end of the secant to the other, that is telling you what the full length is. So please do not try to add anything. The formula that we wrote in the theorem was when it was chopped up into pieces and you had to add them back together. That's not the case here. So look out for that. All right, what would I do here? Anya? You know this one? Okay, so what would it look like?
X squared equals 12 plus 4 and then times
Which one?
times
Okay. So x squared equals 16 times 4, which is 64. So x would equal 8. Remember, I briefly mentioned before, whenever you guys take square roots, think of it as plus or negative, right? But in this situation, the negative 8 wouldn't work. It would just be positive, so don't need to really worry about that there. All right, this one. Who has the formula?
X squared equals 16 plus 2 times 2.
Okay. So that's 18 times 2, 36. So what's the value of x? Nice. This one? Anybody?
6 times 4 equals 3x.
Say it one more time.
6 times 4 equals 3x.
Okay, so 6 times 4 equals 3 times x, which is 24 equals 3x. So what's the value of x? 8. And then who has the last one for us? Keisha?
X plus 3 times 2 equals 4 plus 2 times 4.
Okay. What does the left-hand side of the equation look like? A little bit neater.
3x plus 9
Okay.
equals
Equals what?
44.
Okay. And then what?
X equals 11.6.
11.7 if you're round. Subtract the 9 and divide by 3. Yeah? Alright, so the next page that you guys are going to be working on independently, this is a scattering of both angles and segments. So everything that we learned, the 2 formulas for angles and the 3 on segments, those are all combined on this page. So this is cumulative for this lesson. Go ahead and do as much of this independently as you can. I'm going to leave the first 6 on the board with the answers up. So do those and make sure you get the correct answers. Then I'll scroll down and put the answers up for the bottom 6. Okay? So go ahead and start working on those and check as you are going through that you have the correct answers. two things I'm looking for in this example, x and y. Which one am I required to find first?
Yes.
Why?
I found Y first. I found Y.
Is that a trick question or not?
Is it your question?
I don't even know. I found x first. So in order to, or did I?
No, I found Y.
It's possible. I don't think it actually matters, to be honest. But what I do need to know is this before I can actually proceed. Okay, sometimes they don't give you all the information up front, so you might need to look around a little bit to find some more information to give you some momentum. So what is the most important part of this picture that is easy to miss but is important to use? Semicircle diameter. There's a diameter here. So if I have this diameter and I have the 60 and the 70, what is this little piece right here? Because all those need to add up to 180, right? Okay, so now if you think about it this way, angle X is right here, right? In order to solve for angle X, I need to know arc Y and the arc marked 50 to find X. So actually I do need to find Y first in order to find X. So how would I find Y if I know that this angle is 53? Think about it really carefully. If you want to, you could even draw the picture over here without all the extra lines. Okay, so look, this is all I need. If there are too many lines for you and color coding is too messy, you can always redraw the picture. So what I've drawn above is all that I need to find Y. Okay? So this is my 53. This is Y, arc Y. What's the other arc that I need in order to solve for that variable? Which is 180. So in order to solve for Y, I have the two arcs I need. So the angle would be 53. The big arc is 180. The small arc is Y, and I would divide by 2. So that's how you would use the formula to solve for Y. Draw the picture separate if you need to isolate what's going on. If you want to draw the second circle off to the side, which is what we're using to solve for X, you could do that too. So X is right here. I found that this is 50. Once you guys solve for Y, which is 74. Nope, sorry. That's my bad. I drew it weird. You actually don't need Y to find X because of the diameter. Didn't realize that until I redrew. So if you go like this, X is, again, poorly drawn, but you have this. So actually the other arc that you need to find X is also 180. So to find X, you would do the angle is equal to 180 plus 50 divided by 2. Because the diameter is key to both this angle and then the arc that you would use with that angle, you would use 180 both times. Yes?
Couldn't you also do like an inscribed angle there, and then you get the two other angles of triangles?
Where is an inscribed angle?
60 and 70.
Oh, this one right here?
Yeah.
And use a triangle? Sure, you can do that too. That's a good strategy. Did everybody understand what Brody was just describing? There's a triangle right here. And then this angle right here is using 60 as an inscribed angle. So you do half of 60 to find that one, and then half of 70 to find that one, and use the triangle. But they all add to 180. That's a good strategy too. But if there's too much information in one picture, you can always redraw with only the important information for the one variable you're looking for, and that can make it a little bit easier to see what to do. Questions besides that one? The other ones were okay? Yes? Alright, I'm going to scroll down, put the answers for the bottom 6 on the screen. You guys can be working on those and checking as well. like I was saying when I first introduced this theorem, the angle and the arcs need to line up, don't they? Is the angle they provided lined up with the arcs that they're asking you to use? This one? Is the angle lined up? What angle would I actually need? The one that's next to it. How do I find it? Yeah, they're linear pair. So in order to do your theorem, you just need to find this angle, and to do that, use linear pair of the 65, which is 118? Nope, 108. Wait, what? Yep, sorry. Why is my mental math weird today? Yeah, so you find that angle and then you just apply the formula. That's really the only place where you could get stuck. The rest of it you should be able to figure out. Because again, with that, the way that the arcs and the angle should line up, once you have the correct angle, because they won't always give you the information up front, you have to find everything so it lines up, and then the angle is equal to that plus that divided by 2. So you just write it into the formula and solve. You should get 125 after doing that process. Everything else on that row okay? This one? No, I was asking for this row.
Oh, actually the last one, yes.
Okay, well, what did you write?
16 minus x.
No. It's a secant, right? For a secant, it's full times outside. What's the full length?
16.
And what's the outside part? So you just do 16 times x.
Okay.
16 times x is equal to the tangent squared. When they give you a bracket, they intend you to see it as the full length. So don't try to do add or subtract, just like we saw on the one on the previous page. If they give you the bracket, that's already the full length. So full times the outer segment for a secant, it would just look like that, and then you would evaluate, and then you'd be good from there. Same thing with this one. The bracket, the x is referring to the full length. So the full length is x. So you do no addition or subtraction. It's just x times the outer segment, which is 5. 5x. And then you can do the addition stuff with the other secant. But for this one, you should get 12. Everybody good with that? This one. Are the angle and the chords all lined up? Is everybody able to work with this one okay? Just find the other arc. Yes? Okay. For this one, what concepts from previous days do I bring in to solve this one? There is indeed a triangle. I need something a little more specific than that.
Oh,
Give me some vocabulary here. The chord. What about the chord? It's being bisected? Okay. How do I know it's being bisected? Because the arcs are being bisected? By what? A diameter. That's what the theorem says. If it's a diameter that's bisecting the arc, then you know that the chord is also being bisected. It's a derivation of one of our theorems from day 3, I think. Alright, there's also something else about this that you need in order to proceed. Another thing from day 3. Not only is the chord being bisected by the diameter, something else. They're perpendicular. Alright, you can't just see that there's a right triangle. Sorry, you can't just see there's a triangle and assume that it's a right triangle. Okay? We use the property that the diameter, if it bisects this stuff, it was perpendicular. Okay? So now we have a right triangle, so to find x, you just use Pythagorean theorem. So you get the x. And then if you imagine the picture without the 12 drawn in, if you imagine or redraw the picture without the 12 drawn in, we have 5, 5, 10.9, and then a segment that's missing. What formula do I do if I have chords crisscrossing? Like this one. It's just like this one. So if you take the 12 away, it's just 2 chords that are intersecting, and you know 3 parts, not the 4th. So it's this. We have to find x first using Pythagorean theorem, and then your question just becomes 5, 5, 10.9, and y. And you would do this. Okay? So make sure you're not getting muddled up by too many lines in there. If you need to take them away, feel free, but make sure you're able to see the different theorems pop up, as well as using stuff from previous lessons to help you.